welcome everybody to the grand finale of the Unimog program. We made it here and now enjoy, have a lot of fun with the last lecture by Artem. Thanks, Artem, for being here.
Yeah, thanks for having me. And yeah, sorry I couldn't fully attend the exercise session. So today I want to continue the discussion of some combinatorial consequences of distality for the definable sets. First of all, I want to remind the distal regularity lemma. So recall distal regularity lemma, and let me state it in a slightly different way this time, but an equivalent way. So assume, well, essentially equivalent. Yes, so assume that T is distal. Assume that mu of x, mu of y are two measures, pairwise commuting, definable Kessler measures. Yeah, so assume we're in this situation and assume that E of x is a definable relation. In fact, I don't even need to say this. I'm assuming the whole theory is distal. So then what we have is that the two measures already determine a measure in two variables. Yeah. So then mu tensor mu is the only measure in two variables. So in mxy, yeah, I measure in two variables, which extends the product measure. So the only measure extending mu times mu. Yeah, so recall that this is just the product measure. So it's a measure which is only defined on the Boolean algebra of sets generated by the product sets. So Boolean algebra generated by the sets of the form A of x, direct product P of y, right? So this is the same statement similar to what we discussed at some point early on. So similar to, remember we discussed like when you have two types, for example, when they determine a complete type on two variables. Yeah, so we want to look at like P of x union Q of y, and sometimes it determines a complete type. So this is an analogous statement, but for Kessler measures. So if I have these two measures and with enough assumptions, so commuting definable, we get that they already separately determine the measure in two variables. Yeah. And this is equivalent to the statement of the distal regularity lemma I gave you last time by compactness argument, which I leave as an exercise to exercise. Show that it is equivalent to the previous statement, to the original statement of the distal regularity lemma. Okay. So if you remember that one, what it says is that given E, we could always find two sets E1 given by some disjoint union of boxes, let's say A I of x times B y, yeah, for I less than n, such that, well, and similarly, we have E2, let's say given by the disjoint union of the boxes AI prime times BI prime for I less than n, such that the relation E is sandwiched between them. So we have E1 is contained in E2, is contained, yeah, like this, and they're close in measure. Yeah. So in fact, I should have said for any epsilon greater than 0 here, so that the measure of the difference of E2 and E1 is smaller than epsilon. Yeah. So these are the equivalent statements which can be done, demonstrated by compactness. Okay, so we have this distal regularity lemma, right? And last time we have discussed the Erdős-Hajnal property, which is a property of pseudo-finite dimension rather than measure. Okay, so in the distal case, we already have this measure theoretic consequence, which is strong enough to imply a dimension theoretic consequence. So we have the following corollary. okay, so given a pseudo-finite given a pseudo-finite graph with a distal edge relation, yeah. So let's say E of xy is a distal edge relation in our pseudo-finite graph. There exist internal sets, so there exist A and B, both of positive measure. So mu of A is greater than 0, mu of B is greater than 0, and we have that either A times B is contained in E, or it is disjoint from it. So A times B intersection E is empty. Okay. So if I draw it like this, we have these two parts of the graph, and we are saying we can find a subset here and a subset here, both of positive measure, so that either we have all the possible edges or no edges at all. So we have a complete pair or an empty pair of sets of positive measure. Okay, and this is an immediate consequence of the distal regularity lemma, right? Because if you look, for example, at this statement here, yeah, we can just take, for example, E1. It is a union of boxes, right? And since E1 has to be arbitrarily close in the measure to E itself, there has to be, for example, if E had positive measure, there would have to be a single box, AI times BI for some I, which has positive measure, right? And which is entirely contained in E. So this would give us a complete pair. It has positive measure by Fubini, right? But, well, just because it's a product of two sets. If it is a positive measure, each of those sets has to have positive measure as well. Yeah. Or the other possibility that we find a box of positive measure with no edges at all in it. All right. So this is a property called strong Erdős-Hajnal. Immediately follows from the distal regularity lemma. Now, another exercise. Well, as the name suggests, strong Erdős-Hajnal implies. Oh, I didn't say it. Sorry. So this is called the strong Erdős-Hajnal property. So this is the strong Erdős-Hajnal property. Okay, and as the name suggests, it implies the Erdős-Hajnal property we discussed last time. Okay, so fact or exercise, strong Erdős-Hajnal property implies Erdős-Hajnal. So if you can find a pair of two sets, complete or anti-complete with respect to the edges, both of positive measure, you can use that to find a single set of positive dimension, defined dimension, which is a clique or an anti-clique. Yeah. Okay. So to summarize, it's an interesting situation. So we have the Erdős-Hajnal property both for stable and for distal theories, but it's open for an IP. Yeah, so open problem. Erdős-Hajnal for NIP relations. Yeah, and if you remember, the diagram indicated somehow stable and distal are the two extreme opposite cases of NIP. We know it for both, but in general, it's not clear. Okay. So this immediately tells us there's this one, at least one consequence of distality for pseudo-finite dimension. I want to discuss another one, which is important for various combinatorial applications, namely the so-called generalized incidence bounds. Okay, so let's discuss further consequences of distality for pseudo-finite dimension of definable sets Oops. Okay, so I want to begin by stating a very classical result, Szemerédi-Trotter theorem, which has nothing to do with model theory on the face of it. So it's a very famous result in incidence combinatorics. It says the following: assume you are given n points and n lines on the real plane. Yeah, so just in R2, given n points and n lines on the plane, we can look at the number of incidences. Okay, so let I of PL, well, let me write it like this. Maybe if I take this, denote the set of points by P and the set of lines by L, then we have the incidence relation. So it's a binary relation between points and lines, which just says a point is on a line. So let I be the incidence relation. Okay. Then we have that the number of incidences between these points and lines is bounded by C times n to the power 4/3. Yeah, for some fixed constant C. Well, fixed positive real number C. Okay, so maybe it seems random. Yeah, like why do we care about this number for thirds? So the point is, for us in this discussion is not as much this particular number, but rather the fact that it is strictly better than a general bound. Okay, so because this general result of Erdős fact, in fact, the graph version is due to Cavari, Sosa, and Turan. Namely that for any k, a natural number, if we have a bipartite graph E, let's say contained in V times W, yeah, let's say with the size of both parts VW equal to N, so that E is what is called K free. Okay, so this notation KKK denotes the complete bipartite graph with parts of both parts of size K. Yeah, so by this I mean does not contain the complete bipartite graph with K by K vertices. Okay, so maybe I shouldn't write multiplication. So maybe let's just say, let me just say with both parts of size K. Of size K, right? Then the number of edges, yeah, is slightly smaller than the maximal possible. So, okay, so I said for any K exists epsilon. Excuse me, I'm adding some things as I'm trying to remember what I'm trying to say. So for any K, there exists epsilon bigger than 0. So that if you look at the number of edges of such a graph, it's going to be n to the power 2 minus epsilon. Okay, where this epsilon depends only on K. Yeah, so of course the maximal possible number of edges in a graph with both sides of size n is n square, right? You can have all pairs. So what this is saying, what this is saying is that if I omit some complete bipartite graphs of some fixed size, so you should think about this situation as K being small and fixed, and n grows arbitrarily large. Yeah, so the parts of our graph can be arbitrarily large. Then what you get is that the number of edges is strictly below the maximal possible. It's bounded, the exponent is bounded away from 2 by some positive epsilon. Okay. And also probabilistic argument shows that this is essentially optimal, that this epsilon goes to 0 with k. So in general, epsilon of k goes to 0 as k goes to infinity. Okay, but at least we get some power trade-off, right? Now the point, look, we can view our Szemerédi-Trotter theorem as a special case of this result, but maybe a stronger version of a special case of this result, because if you think about the incidence relation between points and lines, well, there's this property that if you fix any 2 points, they determine at most 1 line through them, right? 2 points can be only incident to 1 line. And what this tells us is that this is a K2-2 free relation. So note that this is K2-2 free. Okay. So it's an instance of the more general fact about graphs, but the exponent here is actually strictly better than the one that can be achieved for general graphs. So this is strictly better. Than for general graphs. Okay. So what this is telling us is that there's some geometric property of the reals, of the field of reals, that is being used here actually. And this is a generalization of this result for over complex numbers instead of real numbers. So on the complex plane instead of the real plane. But again, all the proofs essentially use the fact that the complex numbers can be interpreted in the real numbers. So the field of complex numbers, it just lives on R square. Yeah. So C, you can view C as R square, and it's interpreted in the reals. So somehow for all results of this kind, it seems there is something connecting them to some geometric properties, to something like some real or semi-algebraic geometry. And yeah, so it turns out that it's a general phenomenon, actually, which happens in distal structures. So before I go into that, let me just rephrase it a little bit in terms of pseudo-finite dimension. So we can rephrase the Szemerédi-Trotter theorem. Yeah, I could rephrase it as a pseudo-finite result. So if we look at what we see, we have these exponents, right? So equivalently, we can write it in terms of delta, the coarse pseudo-finite dimension. So which would say that the dimension of lines of the incidence relation of the edges is at most 2/3 the dimension of points plus the dimension of the lines. Okay. So if you think about it, yeah, we take the log. So this n here, n to the power 4/3, what it really stands for, it stands for p to the power 2/3 times l to the power 2/3, essentially. Yeah. Well, plus maybe some smaller order things. So this is how we get this, yeah, just by taking logs and using the properties of logarithms, we see that what it really expresses is that there is some non-trivial bound on the pseudo-finite dimension of the incidence relation in terms of the dimensions of the points and of the lines. Okay. And like I said, this is there's a same phenomena holds in arbitrary distal structures. Maybe not with such an explicit exponent as here, but there is some non-trivial improvement for the statement of this fact. By the way, this fact is really just an application of Cauchy-Schwarz. Like you just try to double count the edges by fibers and use Cauchy-Schwarz. So Szemerédi-Trotter tells you that geometry brings you some improvement over just counting using Cauchy-Schwarz. Okay, and that's what distality does as well. So this statement's okay. I'd like to go to the next slide, unless there are any questions. All right, so now let's go back to distality. So let T be distal, yeah? so T distal. And in fact, it's also local. So we only need actually, maybe let me even not write it like this. Yeah, let me write it. Assume that E is a distal relation. Distal relation, E of xy. We have a distal binary relation in the sense of our earlier discussion. All right. And we want to say that there is a similar improved incidence bound that holds for such relations. So assume it is distal. Okay, then there exists some epsilon greater than 0. Okay, strictly greater than 0, such that for any well, let me follow the notation here. So for any finite sets, let's say for any finite A subset mx, B subset my, yeah. If we look at the restriction, so we take E intersected with A times B. So I only look at those edges of E that go between A and B. So assume that this is KK free. All right. Then we can look at the bound at the number of edges that happen here. So E intersected with A times B. And this is going to be bounded by some constant depending on the relation and K, and then n to the power T minus epsilon for where this T is the bound predicted by the general result for graphs here. So which is the optimal exponent for general graphs. Okay. Let me maybe stress, okay, so what epsilon depends on. So epsilon depends on the relation E itself, or rather on certain numeric parameter associated to E. But okay, so given any distal relation, there's this fixed power saving. So the power is going to be strictly better than the one that holds in general for KKK free graphs. Okay. And I'm not necessarily stating this bound exactly because it's not so important really, yeah. You can look it up, I mean, in any of the references for this. But the point is that there's some non-trivial improvement, and this improvement, it really needs distality. Like for example, you don't have this improvement in stable graphs. Yeah, so remark. If you look at the same incidence relation, but you look at it not over the reals, but over finite fields, let's say in a pseudo-finite field. So let's look at I contained in P times L in an ultra product of finite fields. Finite fields of fixed positive characteristic. Fixed characteristic P. Okay, then a simple construction shows that, namely, you just take all points and all lines. Is going to show that the bound you get is well, you can show that by Cauchy-Schwarz, the bound that you obtain is O of n to the power 3/2, which is, and it is optimal, right? Now, very important realization is that 3/2 is strictly greater than 4/3. Okay, so ponder this. Yeah, because look here, we had in the Szemerédi-Trotter theorem, we had for thirds, right? And this result, okay, I didn't spell it out explicitly, but this result only gives you 3/2. So in fields of positive characteristic, we already have the worst possible scenario, while in fields of characteristic 0, the incidence bound is better, strictly better, at the sense that the exponent is better, not just like some additive constant or something. Okay, the exponent is better. Okay, and so the thing I want you to remember about distality is that it also allows you to get a strictly better bound on the number of edges than in general. Okay. Oh, and this is a theorem of myself. By Fox, Pach, Suk, and others. I mean, there's a whole line, there's a whole industry, this incidence bounds. It's a big area connecting several different areas of mathematics. Okay, but for us, model theoretically, distality seems to be the right context, like maybe the maximal context for characteristic 0 incidence combinatorics. Okay, so we have this. I'm not going to fully prove it, but I want to say a couple of words about how it is proved. So proof idea. The proof idea, okay. Divide and conquer. Okay, so are there any questions? Okay. Even if there are not, I will still say more about it. Yeah, don't worry.
How do you?
So, yeah, even if it's clear. So the point is that, like I mentioned, this general result, Cavarius-Turan, is proved to using Cauchy-Schwarz. You just count basically by fibers. So here, to get something better, we want to use the geometry. We want to use something like a cell decomposition. So this comes. So the idea maybe is if we have like some space and we are trying to count the edges here, maybe what we can try to do is we can try to subdivide the space into some cells, okay? Maybe bounded number of cells. And then we only want to count edges between any two of the smaller cells at a time. And then we have to add it up over all of these pairs of cells. But there's this magic trick that if you choose the sizes of the cells appropriately, and especially you try to do it so that each cell is not split by too many fibers of your edge relation. So if you choose all of these parameters carefully, and then use Cauchy-Schwarz on each of these cells separately, turns out you can actually do better than without using it. And now where do the cells come from? Well, the cells come from a distal cell decomposition. So what we need is somehow is a fractional relaxation. So we need a fractional relaxation, and I put it in quotation marks. Relaxation of the distal cell decomposition. Okay. And this is usually what is called the distal cutting lemma or a cutting lemma. Okay, a cutting lemma. Well, there are other proofs as well, by the way, but this seems to be the one that that works in distal theories. So cutting lemma. So let me recall what the distal cell decomposition says. So it says that if I have a binary relation, E of xy, a distal relation, right? Remember what we said is suppose I have my model mx, yeah, and let's say this is my, and I'm given some finite subset here, let's say B, right? And what we can achieve using distality, so distal cell decomposition, what it says is that we can split M into cells, yeah, so that if inside of each of the cells the phi type is completely determined with respect to B. So if I take any 2 points here, let's say A and A prime, yeah, inside the single cell, we have that A, the phi type, the E type of A over B is equal to the E type of A over A prime over B, yeah, for all A prime in a single cell. So another way to say it is that you cannot split any of the cells using an instance of E with parameters from B. Okay, so this is just distality. Now, what I mean by relaxation, what if we allow now our cells to be split a little bit? Yeah. So what if, so this means cells cannot be split by E, by the fibers of E with parameters from B. So what we want is to relax it, to allow a small fraction, so to allow each cell to be split by a small fraction of the instances E of XB for B variant in our finite set B. Okay. So, and the trade, okay, so we relax the requirement on the cell, and the effect, the positive effect of this is that we need now fewer cells. And in fact, we can bound the number of cells efficiently in terms of the number of parameters being used. Yeah, so relaxation, so the benefit of this is that we'll need fewer cells. Okay, and balancing these two things, somehow the key is to find a careful balance of these two things, so that somehow we have not too many cells which are not split too much by the fibers of E. And if you balance these things carefully, then it's possible to get a trade-off in the exponent when you count the edges. Okay, so it's a bit vague, but I don't want to go into the details of this. I just want to maybe hopefully give you some intuition. And then again, on each pair of cells, carefully chosen like this, you just use the usual Cauchy-Schwarz. Yeah, okay. But what we really need is the existence of the cells. So we need some trace of geometry. And yeah, but it works in any distal theory. All right. Oh, and in distal theory, and hence a posteriori, also in any reduct of a distal theory, right? Which is what will be important for us soon. Okay. So we have this improvement, and again, as you note, since this is a statement about the exponents, yeah, the trade-off in the exponents, this can be viewed as a statement about pseudo-finite dimension again. So what we have is that there's an improved bound on pseudo-finite dimension. So let me write it like this in particular. We can rephrase it in terms of pseudo-finite dimension again. So what we get is that the dimension delta of E is going to be bounded. Well, let me write it like this: E intersected with a product of two pseudo-finite sets, so A times B, yeah, where E is a distal definable relation, and A and B are pseudo-finite sets, ultra products of finite sets. And such that we're assuming that E intersection with A times B is K, let's say 2S3. Yeah, I mean, it's more general, but we will only this bound somehow is needed in what I'm going to talk after. But you have an improvement for any KKK. So, okay, so this can be bounded by the maximum of the dimensions of A plus 1/2 the dimension of B, okay, minus some epsilon. strictly positive epsilon, yeah, greater than 0. Delta A minus 1/2 delta B. Okay, I have this. And maximum, because we also have to consider the situation when the sets are very unbalanced. When, for example, A is much bigger than B. So I also add delta A and I also add delta B. Okay. So this is a sort of finite rephrasement of this exponent trade-off, or power saving, sometimes it's called. Okay. So this is what distality gives us. Now, I want to discuss an application of this, which combines both distality and stability all at once. Well, and additive combinatorics and other things also. So I want to talk about the sum product phenomenon, or phenomena. I guess it's there are a lot of variations of this theme now. So the first result, I guess, yeah. So the first instance of that initiated this whole direction is due to Erdős and Szemerédi. Erdős-Szemerédi. Okay. So it's a remarkable fact. There exists a constant, well, two constants, C and epsilon, both greater than 0, such that for any finite set of the reals, so for any A subset of the reals, we have that the maximum of the sizes of the product set and the sum set is strictly larger in the sense of the exponent than the size of the set A itself. Okay. And here what we mean, this is just the set of all products of the form AB for AB elements of A. And this is similarly for sums, right? So A plus B for all A, B, and A. So there is some expansion happening here. Take any set, take all products, or take all sums, and you get a strictly larger set. Yeah. This maximum here is important because each of these sets separately can be small. Like if you take, for example, if you take an arithmetic progression and you look at the sums of elements of this arithmetic progression, most of them are still in the arithmetic progression. If you ignore a few at the end, yeah. And similarly for the geometric progression, you get this for products. The products of the majority of the elements are still in the set, except for a few at the end. So for neither of those separately, you would get this. But what it's telling us is that somehow plus and times are orthogonal operations, or maybe non-exogenous operations, that if you combine both, at least one of them has to give you growth. Okay. So this is Erdős-Szemerédi. And let me actually quickly prove it, because it follows very quickly from the Szemerédi-Trotter theorem. So the incidence bound, and which also hints at much deeper connections between this expansion phenomena and incidence bounds. This is proved due to Elekes. So we have this points, right? Let's say I have a set of points and a set of lines, right? So, well, I need to define some points and some lines. So let's define the set of points of the following form. So these are points on the plane, A plus B, C times D, where all A, B, C, D are in A. Yeah. So these are points, subset of R square. And similarly define lines to be of the form A, Y is equal to A, X minus B, for A, B, and A. Okay. So given our initial set A of real numbers, we define some points and some lines from it, okay, in this particular manner. Then we have that the number of lines is A square, okay, and the number of points defined in this way is a plus a, the cardinality of a plus a times the cardinality of a times a. Okay, so you can see this just from the definitions. Now, every line of the form a x minus b in L contains the points b plus x, a times x for x in a. Okay, so it contains all points like this. So we get that the number of, well, let's call this line L, little l, for example. So we get that little l intersected with P is greater or equal than A itself, right? Because it contains all points of that form for any x in A. So this gives us that cardinality is at least the same as A. And so we get that the number of incidences between these points and these lines is at least the number of lines times A. Okay, so this is, so we just have this bound from the way we defined the points and the lines, but now we can also invoke the Szemerédi-Trotter theorem. So by Szemerédi-Trotter, what we get is that the number of incidences is bounded by some constant, yeah, C. So this is where the constant comes from. C times P, the number of points, times the number of lines, both to the power 2/3, plus the number of points, plus the number of lines. So these are the smaller order, well, the unbalanced case things which are typically smaller order in the interesting case. Okay, so we have a lower bound and we have an upper bound. And now we just can compare them and the previous observations. So we get that if I look at A times A times the cardinality of A plus A, okay? So this is the cardinality of P times A square. This is the cardinality of L. Okay. And now we take all of, oops, now we take all of this to the power 2/3, yeah? And we get that this grows as A cube. Yeah, so by combining those two bounds. Okay, and from this, by arithmetic, we deduce that the maximum of A plus A and versus the cardinality of the product set, A times A, grows like A to the power 5/4. Okay, and 5/4 is bigger than 1. So we get the epsilon of the form 1/4 here. Okay, so this proof gives epsilon 1/4, but there are many improvements on this by now. It is expected actually that the exponent should be arbitrarily close to 2 here. Yeah, but we get at least some non-trivial improvement from this very neat argument. Okay. So this is this shows that you get expansion just for addition and multiplication combined. Okay. Now this phenomenon is much more general. So what we have is that a more general result of Elekes and Ranyai generalizes it from just addition multiplication to typical polynomials. Yeah? So the typical polynomial has the similar expansion properties. So namely, we have so Elekes-Ranyai. We have that given a polynomial in 2 variables, okay, x, y, let this be a polynomial. Yeah. Then for all finite sets, AB, finite subsets of R, let's say of size n, if we look at the image, so we look at F, you apply it to every pair from AB, and the number of points you get this way is going to be to grow at least as n to the power 4/3 up to some constant. Okay. Okay, so you say, of course, this can't be true, right? Because if my polynomial is just addition or just multiplication, I said earlier that you don't get the expansion. So we have to exclude those cases. So unless F is of very special form, so F is either of the form G of H of X plus I of Y, or form G of H of X times I of Y. So essentially, it's either controlled by addition of univariate polynomials or by multiplication. So it doesn't mix the addition multiplication in any non-trivial way. Yeah? But as long as it does, again, we have the expansion. Okay. And finally, well, not finally, but a conceptual generalization of this, which somehow later was realized to that they actually how model theory comes into this kind of considerations. So there is this influential result of Elekes-Szabó, which generalizes it from polynomials to algebraic varieties of, well, surfaces more precisely in 3 variables. So for any, let me state it in the following form, just to keep it simple. So for any algebraic surface, R of x1, x2, x3, let's say in R cube, okay? And we assume that it is somewhat non-trivial in the sense that for any, so that the projection onto any 2 coordinates is finite to 1. Okay, so we want to exclude some trivial situations, like when, for example, my surface is all of R3. Okay, so for any thing like this, so if you fix 2 variables, there are few choices for the 3rd variable, finitely many choices for the remaining variable, for any permutation of the variables. We have that exactly one of the following holds. Okay, the first possibility is that there exists some gamma greater than 0, okay, such that for any finite AI subsets of reals of size n, if we intersect our relation R with the grid A1 times A2 times A3, okay, so a product of 3 finite sets where R is a definable relation, well, algebraic surface in this case, but like we're in the same situation, we're intersecting a definable set with some finite sets. And we're asking about the asymptotic growth. So the first possibility is that this is bounded by n to the power 2 minus gamma. Okay. So note that it can be at most n square, right? Because we already said by assumption that if you fix 2 coordinates of R, there are only finitely many choices for the remaining one, right? But then this means that you can choose 2 coordinates freely. This gives us n square, yeah, and maybe times some constant, which takes into account the possibilities for the 3rd coordinate. So it could be at most n square, and here we are saying that it's strictly less than maximum. So it's strictly less than the maximum possible size of intersections with grids. This is possibility 1, or possibility 2 is that our relation is somehow closely connected to a group, or there exists well, in the locally here, at least, there exist open sets. Oops, excuse me. There exist open sets, UI, subsets of the reals, and V, subset of R, containing 0. Okay, and bijections, which are even analytic. Okay, so let me write it: analytic bijections, pi I from UI to V. Okay, such that if we look at when R holds, so R of x1, x2, x3 holds, if and only if we have that pi1 of x1 plus pi2 of x2 plus pi3 of x3 is equal to 0. Yeah, so this holds simultaneously for all on the whole neighborhood. So for all xi in UI. Okay. So the first possibility, the sizes of the intersections with grids are strictly below maximum, have this power saving, or if your relation, arbitrary relation, right? Like just an arbitrary relation, if it has maximal intersections with grids, then it already has to be essentially the graph of addition in the additive group of the reals. Yeah, so it's somehow strongly connected to the group. Either we have power saving, or the relation is strongly connected to a definable group. So this, yeah, any questions about this? All right, so and turns out that this is a very general principle, which by now a lot of people have worked on, and there are a lot of generalizations. Khrushchevsky realized that model theoretic ideas play an important role here, in particular something called group configuration, which allows you to find a definable group starting with some so in fact, Elekes-Szabó have rediscovered this in a way.
You lagged for a second.
Oh, okay. Yeah, sorry. So what I was saying is that this ideas of pseudo-finite dimension playing a role, as well as model theoretic group configuration theorem, they somehow play a role here. And okay, morally, this is a generalization of the sum product phenomena. So I just gave you a proof, right? How you can use the bound for points and lines. And this way, but here we had the luxury that we could very explicitly define our points and lines. In general, you cannot produce something like this in any obvious manner if you are only given, let's say, an algebraic surface, or more generally a definable set in some tame situation. So, but the idea roughly is the same. So there are these two cases where you have this power saving, which would correspond to the case of the when Szemerédi-Trotter theorem can be applied, or you have to somehow connect your relation to a group in a strong form. I don't have too much time, unfortunately, left to say much more about it, but let me just state maybe. Okay, so like I said, there are many generalizations of this result. So many generalizations. Been a lot of activity in the last decade. In particular, it holds in any stable structure which admits a distal expansion. Okay, and by it holds, I should probably put holds in quotation marks because I haven't stated any precise theorem. Yeah. So what I mean by this is that in a similar result, you can assume that this R here is of any arity. So it could be like Rx1 through Xn. And all we want is that it is definable in a distal structure, in a stable structure with a distal expansion. Maybe there should be some name for this combination. I don't know. Distal stable structure with a distal expansion. The distal expansion, okay? And the second part has to be modified in the sense that here we are just connecting to addition, right? Just plus in the reals. In general, arbitrary definable abelian groups can appear in this kind of statement. And even nilpotent in the more general versions of this statement, but I'm not going to go there. So this part 2, yeah, we have to reformulate it by saying that, let me try to maybe erase this statement like this and hand wave just for a couple more minutes. So what we have to put in 2 is that R, so possibility 2 is that R in a correspondence, something like finite to finite correspondence, oh, here it should be n minus gamma now. Oh, I shouldn't use n, excuse me. This was, let's do it k, and I put k here as well. Correspondence with the relation x1 plus plus xk is equal to 0 in some type definable abelian group. Okay. So in the first case, we just had in the original case we just had addition in the reals, in what I stated earlier. But now we have this more general version, right? And finite to finite correspondence, these are the PIs we had before. So before they were bijections, now they're going to be something a bit more general. The more precise statement would be that there is a generic tuple for the relation R, generic in the sense of forking and stable theories, which is interalgebraic with a generic tuple in a group, in some type definable group G. Okay, so maybe this just indicates some intuition. And I guess also this is not a okay, so right, okay, so this is one of these generalizations where we try to generalize which classes of structures are allowed. Yeah? So they show there's really model theoretic reasons for this to work. There are many other generalizations. I should mention an important one by Martin Bayes and Emmanuel Brouillard, where they generalize to arbitrary relations definable in algebraically closed fields of characteristic 0. As I mentioned earlier, characteristic P wouldn't work actually, because in characteristic P, the incidence bounds don't hold. There are no improved incidence bounds. So there might be some other versions, yeah, but a priori it doesn't hold in this form at least. And the proof is an interesting combination of the pseudo-finite counting dimension, which was realized by Khrushchevsky, plus some geometric stability theory, like group configurations, some ideas from matroids, local modularity plays a role. So it's like a very stability theoretic, geometric stability type of argument, plus incidence bounds which come from distality. That's why we need the distal expansion somehow. So all of the things come very nicely into interact in this type of phenomena. Okay, but I think I should probably stop here. So I'll be happy to, if you want to email me or something, or maybe I talk to the organizers. I can provide some links to like where you can read more about this part, because it was very hand wavy. Okay, but anyways, I'll stop here. So thank you very much.
Thanks a lot, Artem. Do you guys have questions?
Hi, Artem, can you hear me?
Yes, yes.
Could you go back to the slide on Zarankiewicz problem for distal structures?
Yes, this one. Yeah.
When you say that T is the optimal exponent for general graphs, is T known in general, or is that just, is it known?
Okay, optimal here I should put in quotation marks. It's optimal from some point of view. Yeah, it's optimal. Okay, let me go back to this. So what I mean by this is that this epsilon here, the part that we know is optimal is that it has to get closer and closer to 0 with k. That it goes to 0 with k. That's kind of the, yeah, it's not known. Sorry, the problem in general is open, of course. The Chernikov problem is not solved. So here, optimal, I mean, up in a very crude sense, which is like somehow relevant for this discussion, okay? But like the exact exponents in general are not known.
Okay, thank you.
Any other questions?
So you made a throwaway comment last time about expander graphs not being distal expansion. Can you expand on that, or maybe say how it relates to this at all?
Yes. Let me expand on the expanders. Yeah. Yes. So let's see. Okay, expander graphs. If you don't mind, I'm not going to define precisely but I want to communicate. So the idea really that this is somehow sparse graphs, which can be viewed as being somewhat sufficiently random. So sparse, but well connected or sufficiently random. Okay. The point, right. In fact, we need very little randomness for it to work. What we're really trying to do is contradict strong Erdős-Hajnal. So they fail strong Erdős-Hajnal property, right? So let me maybe try to explain pictorially. So like, assume I have a bipartite graph, okay? Assume it's very sparse. So this is the first part, sparse. So sparsity would ensure that if I take any two sets of non-trivial measure, of positive measure, because it is sparse, it is very unlikely that I actually have all possible edges between them. Yeah, because somehow this would, if I have like a positive fraction, positive measure subgraph with all edges, this was definitely shouldn't be sparse, right? Like you don't expect this to happen. So sparsity part rules out the possibility of a complete pair. On the other hand, the pseudo-random part rules out the possibility of an empty pair, because like assume I have edges in my graph with some probability, right? Like that let's say I pick a graph at random with some non-trivial probability of having an edge. But then if I take any two sufficiently large sets, there would have to be an edge between them. Yeah, like if I have two sets of positive measure, if there's any randomness at all, I'm likely to find an edge between them. And this would rule out empty pairs. Okay, so this combination of sparsity rules out complete pairs and pseudo-randomness rules out empty pairs. Yeah. So combined, this tells us that the strong Erdős-Hajnal property cannot hold in graphs with these two properties. And now, if you choose, well, if you make sense of all of these words in some careful manner, basically whatever you come up with is going to contradict strong Erdős-Hajnal. Yeah, and some typical important example explicit constructions. I mean, you can construct expander graphs probabilistically, or it can be constructed explicitly. So, for example, Ramanujan graphs, it's a very important construction with strong form of expansion. In fact, typically people, typically people consider expander graphs as graphs of bounded degree. So that would immediately rule out, of course, complete pairs, right? So what we need here is somehow a sequence of graphs where the degree is growing slowly, but yeah, so expansion is somehow growing slowly in a sequence. And if you take just a disjoint union, let's say, of a family of graphs like this, then it's not going to satisfy strong Erdős-Hajnal if the parameters are chosen correctly. And this is more general phenomenon, in fact, because similarly, if you go back to the fields, right, like the example of why ACFP fails strong Erdős-Hajnal. For a while, this was the only example where we knew that it has no distal expansion, a stable theory without a distal expansion. But the reason there is actually the same. The point is that over finite fields, the incidence relation between points and lines has the expander properties. Like it's sparse, it's even bounded degree, right? Because again, 2 points determine a line. So you definitely cannot have 2 sets with all edges between them of size bigger than 2. But also it's essentially pseudo-random. So then you can never have an empty pair, because if you have any 2 sets large enough, there will be a point in one and a line in the other, which are incident. Yeah. So in fact, expansion explains failure of strong Erdős-Hajnal in a CFP as well, in a more conceptual manner. And as far as I'm concerned, I mean, failure, just if you take the property, the failure of strong Erdős-Hajnal, by itself, it could be viewed as a very weak form of expansion. The only reason in the appropriate expansion regime for the failure of strong Erdős-Hajnal. And this is the only reason we know currently to avoid existence of distal expansion. It actually would be very interesting to know if it's possible, if there could be other reasons for this, for the failure of a distal expansion.
Okay, thanks.
Okay, but yeah.
Any other questions? Not at this point, it seems. So Artem, thanks a lot for your really beautiful course. Thanks for being here in the mornings.
Thank you. Thank you. Yeah, and if I may just say, feel free to email me. Like if you want a reference for something I said, or if I said some nonsense, or yeah, like I'm very happy to if there is some interest in this. Yeah. It's an active area, by the way, so there are many open questions, etc. I think like if you're looking for a problem to work on, there are a lot of things to do somehow. Yeah.
Thank you.